The conventional definition of the outer edge of the habitable zone relies on the greenhouse effect due to CO2 offsetting the effects of reduced installation. The maximum amount of greenhouse effect that is possible is determined by either the radiative max greenhouse limit or the thermodynamic CO2 limits. However, these do not take cognizance of geochemical constraints on the amount of carbon dioxide that can be present in the atmosphere. So to complete the assessment of the outer edge of the habitable zone, it's necessary to look into the sources and sinks of carbon dioxide. The model that we employ couples a simple model of outgassing from the planetary interior to a silicate weathering model based on Mayer and Chamberlain of the sort that R.J. Graham and I discussed in connection with the outer edge of the habitable zone. These are linked through an energy balanced atmosphere, which gives us the surface precipitation and temperature conditions. The decay of radionuclides U-238 and thorium-232 are the primary pacemakers of the long-term habitability. The outgassing is parameterized in terms of geothermal heat flux. We assume efficient crustal recycling. Now on to some results. In each of these results, we'll show the surface temperature on the vertical axis, and the horizontal axis is time in gigayears going out to 100 billion years. I show results for 4 cases. One case with the same concentration of long-lived radionuclides as the Earth has, and another case which is deficient in radionuclides. The justification for looking at the deficient case, the depleted case, is that uranium and thorium are generated by very exotic events, even events as exotic as collapsars. So it's by no means certain that the concentration of uranium and thorium is uniform across planet-forming regions. Within each of those situations, I show results for 1 Earth radius and 2 Earth radii, super Earth. So in this fiducial case with 1 Earth radius and Earth-like radionuclides, you can see that actually you maintain habitability, you maintain above freezing temperatures out to beyond, somewhat beyond 20 billion years. But that still is a limit. You get a little bit more habitability time if you go out to a super Earth case. And then if you go to the depleted cases, your habitability time is contracted quite severely. And that's even without seafloor weathering. So now let's take a look at what happens when we turn on the seafloor weathering. Seafloor weathering allows the last bits of CO2 to be sucked out of the atmosphere in cold conditions, leading to these rather dramatic cliff-like features that limit habitability time to about 20 billion years in the most favorable case, down to well under 5 billion years in the cases with depleted radionuclides. So now if we look further out in the habitable zone, to where the installation is maybe 80%, of Earth-like installation, you constrict the habitability time quite severely, even in the case where the seafloor weathering is not taken into account. So the upshot is that, if you're relying on heating by radionuclides alone, by uranium and thorium, there's no way that an M-star planet will get to live out anything like its potential trillion years of habitability. It will be subject to tectonic freeze out long before the star actually dwindles away and becomes dimmer and dimmer and dimmer. And there are some cases towards the outer edge of the habitable zone where the tectonic freeze out becomes a limit even for somewhat higher mass stars, K stars, and in some cases even G stars. Now for the crazy stuff. It actually takes very little energy to cook CO2 out of limestone. It's just that natural planetary processes are very, very inefficient at doing this. In fact, the current worldwide cement production releases a half gigaton of carbon annually just from the calcination reaction alone, which is enough to offset estimated global silicate weathering. Now, you still need to react CaO, which is quicklime, with silica to form an actual stable silicate. But basically, if an M-star civilization reaches a technological level similar to our own before tectonic freeze out, it can keep its planet from freezing out as long as it wants. Now, with natural non-technological processes, there's also the possibility of extending habitability time with tidal heating, which is a subject for another talk. Thank you for listening, and I'm looking forward to the subsequent discussions.